finishing up this collisions worksheet. If a 50 kilogram student on nearly frictionless rollerblades, initially at rest, catches a 10 kilogram medicine ball traveling at 8 meters per second. So we'll draw our student here on rollerblades. All right, standing there, ball's incoming. And then after the collision, the ball and the student, right, come one. So the speed of the ball incoming is 8.0 meters per second, 10 kilograms. The student is 50 kilograms. After the collision, they stick together. So P before equals P after. So this is a lot like what we did in number 3, right? All of the momentum initially, P before, it's all in that incoming ball. So it's 10 kilograms times 8 meters per second. Incoming momentum of the ball. This one's at rest, so this one's momentum is 0, so plus 0. After the collision, we treat these as one object. Treat as one object with a mass of 60 kg, right? Because they stick together. It's all one object now. Let me put my focus lock on here. All right, so after the collision, it's 60 kilograms that is moving at an unknown velocity v. So that was plus 0 there. So what we have is 10 times 8 is 80 equals 60 times v. Divide both sides by 60. You get v equals, I thought it was 1.2, was it? I don't remember now. 1.3 again. And in this case, the velocity came out positive because my initial velocity of the ball was positive. So it was a positive momentum initially. So we got to have a positive momentum of the system after the fact. All right, this is one of my old favorites, this problem here. This is something that's depicted often in movies where, you know, there's some sort of space battle or emergency or something, and, you know, the astronaut or the whoever, whatever it might be, might have to try to move through space. So to do that, they throw something. All right, so it ultimately is asking us for how long will it take, how fast will we move. All right, so let's just start off with the before and after. So before, the astronaut's just sitting there with the wrench, not moving. After, what happens is the astronaut throws the wrench, right? It's all kind of silly. It gets thrown to some velocity. That velocity is 12 meters per second, and since the way I drew it, it's going that way, I'm going to make it negative 12. That means the astronaut is going to have momentum the other way, right? But it's going to be a lot less, because this is 1 kilogram, the astronaut is 140 kilograms. So P before equals P after. Before the astronaut throws the wrench, the momentum here is actually 0 because nothing's moving. After the astronaut throws the wrench has a momentum of 1 kilogram times negative 12 meters per second. And then the astronaut's going to have their momentum of 140 kilograms times the unknown speed. Now, since these two momentums have to add up to equal 0, meaning the final total momentum of the system afterwards has to be 0, then this product and this product must be equal to each other, but opposite in magnitude. So this is 0 equals 12, it's negative 12, plus 140 times v. So 140 times v, bring the 12 over to the other side, you get 12 equals 140 v. Has to be 140 times smaller the mass is 140 times bigger, therefore the speed must be 140 times smaller when they have the same force acting on them. So speed is going to be 0.086 meters per second. And then to find how long it will take to go 10 meters, right? So the astronaut starting, let's say the astronaut is here, right? And they got to move 10 meters to get to the station at a rate of, right? At a rate of 0.86 seconds, delta x. So v equals delta x over t. It's just going to be a constant velocity, so we got to solve for v. So cross multiply here. You get t equals delta x over v. So t equals 10 meters divided by 0.86 meters per second, or about 117 seconds. So it'll get there eventually. The astronaut will get to the station eventually, but it'll take a minute. 1 kilogram block and a 2 kilogram 5 kilogram spring compressed between them. All right. So this is very similar. 2 blocks, spring between them. 1.0, 2.5. It's all at rest. After they spring off, the 1 kilogram flies off at 3 meters per second. The 2.5 kilogram goes off at some unknown speed. It's going to have to go that way though, because we know that the initial momentum, P before, total initial momentum has to be 0. Negative 1.0 kilograms. That's terrible. 1.0 kilograms times negative 3.0 meters per second. That's the momentum of block 1. Momentum of block 2 is 2.5 kilograms times the unknown v. So basically, they have to be equal and opposite to each other, right? This is negative 3, 2.5 times v also has to be 3, but positive 3, so they add up to be 0. So 0 equals negative 3 plus 2.5 v. Bring this over here. You get 3 equals 2.5 v. V equals 3 over 2.5, which equals 1.2 meters per second. So the big block moves at 1.2 meters per second. It's got to be slower because it's 2.5 times the mass, so it's got to be 2.5 times slower. All right, I think the bell's going to ring here shortly. I might have time. I just want to go back and do that very first example for you. All right, P before equals P after. So on the left side here, we've got 1.0 kilograms times positive 2.0 meters per second plus 1.5 kilograms times negative 1.0 meters per second. So that's the total initial momentum. You find the momentum of each of them individually and add them together. Don't forget the fact that this one's got to be negative because it's got a negative momentum, so I'll put the negative velocity in there. This one over here on the right, you've got 1.0 kilograms, so this is the momentum of this one after the collision. And then this one times the unknown velocity. Don't put a sign on that. You don't know if it's going to be positive or negative, so don't put a sign on it. You just got to do the math. So it's 2 minus 1.5 equals negative 1.5 plus 1.5 times v. So you got to be careful with your signs big time. That's very important, right? This is moving to the left. Those got to be negative. So 2 minus 1.5 is 0.5. We're going to add I guess I could have brought this over here and just canceled it out, right? And that would have been smart. Add 1.5 to each side, so it ends up being 2.0 equals 1.5v. Divide both sides by 1.5, so 2.0 divided by 1.5 equals v. V equals 2 divided by 1.5, which is 1.3 meters per second. And it comes out positive, the answer, right? If it had come out negative, then it would have been still moving forward, but it doesn't. It comes out positive, so it's moving backwards. They hit, and the bigger one does bounce backwards.